So it's already recording.
It is recording. So if I see here.
There's one attendee, Rosie.
Okay. All right. I guess we can start. All right. Hi, everyone. Welcome to the session, to this sponsored session by Intel. I am Rania Hussein from the University of Washington, and I have my colleague, Dr. Pablo Ojuna from LabsLand. We will be sharing with you our experience in setting the remote FPGA lab using Intel's FPGA boards. Just to note, the description of the session has two parts. The first part is actually will be covered in another session fully by Larry Landis of Intel, and I think it's I'm not sure about the time, but it's under the scheduled event, so it's happening later. And in that meeting, he will be going over the RTL and the first part of the description. So basically, this session is the second part of the description that you see on the session description. So I will start by with my colleague Pablo. So please take it from here, Pablo.
Thank you. Also, first of all, I see that there are two participants, and there is a. We do not know if you have access to the chat functionality here. If you do not, you can always use the Pathable, I don't know how to pronounce it, the website, where in this session there is like a chat option, and in that chat option you can write messages and we can see them. So feel free to write us in either chat, wherever you can write. So I'm going to start sharing the presentation. Okay. So as Professor Hussein said, this workshop is going to be focused on the distributed FPGA laboratory between University of Washington and other universities using the LabsLand network, and presented by Intel. The outline is going to be, first, we are going to explain a little bit about remote laboratories, then about the LabsLand network, then the University of Washington experience using these remote laboratories, and we will do like one or two demos, and then we have the Q&A. So the first point is remote laboratories. For those of you who are not familiar with them, a remote laboratory is essentially a system that allows students to access remotely laboratories which are located somewhere else on the internet. So for example, here we can see that the student can be using like the computer. This is pre-COVID, like that's why you can see them like in the same classroom and all this. And these students are using this tool to write code and so on, and then they can send it to a real FPGA, for example, or a real device somewhere else on the internet. In the case of LabsLand, those laboratories are located typically in partner universities or in our offices. So one example of a remote laboratory is the Arduino robot. I'm not going to explain it in too much detail because this session is focused on the FPGA laboratory, but just to show another example, in this case, we can see here how the robot looks. Like we have a set of robots, we have cameras and so on, and those robots can be controlled remotely. So as you can see in this video, once I can control the robot, I can move the robot remotely, and I can put it in certain location, and then I can send a program that I just made before. So I will see during like 10 seconds. It will take some time to program the code inside the robot, in the microcontroller, the Arduino microcontroller that is in the robot. And then the robot will start following the instructions and showing like the serial monitor messages and so on. So the student is always accessing a real robot somewhere else, not a simulation or anything like that. Now, those are remote laboratories. Now we're going to explain a little bit about the LabsLand network. That robot that you saw is in like the LabsLand offices in Spain, but LabsLand is a global network of real laboratories available online. Like for example, that same robot is located in many different locations. We have it in Costa Rica, for example. We have it in South Africa. It's also in Colombia. It's going to be at the University of Washington next month. So we have a pool of different copies of the same laboratory in multiple locations. And this is the case of Arduino robots, but we also have Arduino boards like Arduino Uno with different types of LEDs like actuators and like other types of components. We have electronics laboratories, like quite advanced ones, like where you can build circuits, like with the put resistors and so on, connect them, and capacitors and op-amps and transistors, and connect them in a real environment, and you will see what happens with a real oscilloscope and so on in a real environment. And again, as always, like we always have these laboratories located in multiple locations, like in this case in the University of Georgia, in TU Dortmund in Germany, in UNED in Costa Rica, and in the University of Deusto in Spain. We have it. We also have obviously the Intel FPGA laboratory. I'm not going to talk about this laboratory too much because Professor Hussein is going to explain more in detail this laboratory, but like she's Professor Hussein at the University of Washington, but this same type of laboratory, we have it at the University of Michigan, at Monash, Malaysia, at UPNA in Spain, and at Unifesp in Brazil. So students love it because they see that they are using real equipment and not like a simulation, and they don't have to have the equipment all the time. They can use it 24/7 at home, like anywhere at any time. In LabsLand, we also have many other types of laboratories, like for example, biology, like physics, and these are a different type of laboratory. These are what we call the ultra concurrent laboratories. This means that the students can access pre-recorded experiences of these laboratories. So for example, in the case of reactivity, you have like a strontium and a particular no absorber and 15 millimeters and like certain parameters. You can choose between 1,300 combinations, and we have multiple recordings for each particular combination. So we have over 6,000 combinations of what is possible. So in this case, like you will see a particular video pre-recorded in the past, but it's once again in a real environment. So it's always real laboratories, but always through the internet. But sometimes it's real time, as the ones that I presented before, the FPGA, Arduino, and so on. Sometimes it's pre-recorded, and in pre-recorded we have 3D printers. We have valves like a centrifugal pump. This is a new laboratory in Italy. We have a chemistry at the University of Georgia. We have petroleum engineering in Germany. And we are building many more laboratories of physics, chemistry, and so on, like for example, in South Africa or in Costa Rica. So as I said, like there are the two types: the real-time laboratories by the LabsLand network, like which are the traditional remote laboratories, and we always have multiple copies in multiple locations of each laboratory, and that includes the FPGA, which is what Professor Hussein is going to present, and also the ultra-concurrent approach, which is like what we typically use in physics, biology, chemistry, and other fields. On top of this, LabsLand, as I said before, is a network, meaning that it's like a marketplace. So we act as a network between different universities and schools, and also other universities who are the laboratory providers. So we separate it in two categories. One is the laboratory consumers. Laboratory consumers are those who do not have any LabsLand equipment. They don't purchase hardware from us. They do not develop their own laboratories. But they just say like, okay, I want to use this FPGA laboratory, for example. So like using like a subscription model is like a software as a service kind of thing, where you connect directly to some equipment which is located like somewhere else, and you can administrate your own space with your own groups and learning management systems and all these things. So you can control your own students, but basically you are purchasing, well, you're buying is access to those laboratories which are in the network. At the same time, we have the laboratory providers, like the University of Washington. The laboratory providers are those universities who are hosting laboratories of LabsLand or who are developing laboratories with LabsLand, like the ultra concurrent ones and so on. And we have like a compensation mechanism and so on. Right now, we are working as providers with 27 universities in 14 countries in all the continents, from obviously like in the US, or like Spain, Italy, Australia, like Brazil, Germany, Costa Rica, and so on. So with this, I'm going to give the floor to Professor Hussein so that she can also explain in this like in the whole LabsLand network, there is like this sub-network of the FPGA laboratories, and it's a growing community and with many awards and so on. So I want to present to give the floor to Professor Hussein so she can continue from that point.
Thank you, Pablo. So I'll start sharing my screen. Okay. All right, so welcome to the second part of the session. I want to start by thanking Intel for inviting us and sponsoring this session so we can share with you our experience with what me as an educator would like to call the next generation of engineering labs. So this actually started at the University of Washington in response to the COVID-19 and the inconvenience that happened to educators pretty much everywhere, where the courses that rely on hands-on experience and actual physical hardware, how can we get the hardware to the students? How can we provide students the same experience that they would have had if they were on campus? And so the idea, I teach at the University of Washington in the Electrical and Computer Engineering department. I teach embedded systems courses and I teach digital design. So my course is a junior level course on digital design using FPGA, and we use Intel's DE1 SoC boards. And so when the COVID hit, how can, as I mentioned, how can the students get the boards? Shipping, some students, our international students, had difficulty receiving the hardware. And so it was just an inconvenient way. And it's not only the boards, actually. My course interfaces the FPGA board with peripherals. So how can not just shipping boards, but also peripherals, and how it just was so inconvenient. So this came, this distributed FPGA lab between University of Washington and the other universities. This is what our network looks like. And as you can see, we are the University of Washington and University of Michigan. We are both in the United States, and then UNIFISP in Brazil, UPNA in Spain, and Monash University of Malaysia. So between the 5 of us, we all have FPGA boards in our institutions, and our students are using our own boards as well as each other's boards. And so the concept of load sharing, I teach larger class. So my class is usually around 60 students. So, and I have at the University of Washington in autumn 2020, when the distributed FPGA lab just deployed it and for the first time, how many boards can I give to students, and how many boards is enough? And so the idea of, of finding a solution that can allow me to still set up few boards on site, and instead of just allowing my own students only, to access our web server at UW and access the hardware. That was a solution, but then I was concerned about the load sharing problem with large class. How can I manage this? And so that's when the LabsLand network was a perfect solution, because of I don't need to worry about my own lab, but I know that my students can access labs at Monash University or UBNA, or UNIFESP or UMichigan. And so while we were in the process of deploying at University of Washington, my students were using actually the boards at UBNA until our boards were up and running. Then the students started using the boards at University of Washington, where they get a priority. And then if they are all used, then they go and get access to boards within the network. So it was a perfect solution. This is what the remote FPGA lab at University of Washington looks like. And as you can see here, it's this structure has the Intel's FPGA boards. And in addition to the mechanism of capturing the output by a camera, and then connected to, this will be streamed to web interface, and you will see that shortly in a demo. And this is a close-up of our FPGA lab at University of Washington. Currently, we are expanding, and I will talk about this as our future work. I briefly mentioned, with regard to my course as an example, it wasn't enough just to have access to only the FPGA boards. There, some features were needed. And so we worked with LabsLand on developing those features to make them available to my students, but also to all users in the network. And so we worked on adding a breadboard so that students can interface an external circuitry with the FPGA board. And we also worked on audio. How can we capture audio from the FPGA? And full experience, as you can see, using VGA board, using VGA display, and in addition to some controllers, if students want to work on projects like game development, for example. So this is what is also supported on the network. If you try logging in and try the remote lab, which we will provide you with a link to test at the end, you are able to use any of these either standard basic keys or interfacing a breadboard with the FPGA. And in that case, we have virtual part combined with real part. The real part is what is the camera is capturing, which is the FPGA boards. And then some parts are emulated, like the virtual keys. Or we have the VGA or the we have keyboard also, and also a joystick. Okay, so any of these are supported. And I know that I've been talking a lot. It's time to see a live demo running a very basic program on real FPGA at University of Washington from LabsLand web interface. So I'm gonna pass it to Pablo to run the demo, please.
Okay. Can you see my screen?
Yes.
Okay, so for the demo, first of all, as Ryan said, we are going to send you a link through the chat, so you can register and create an account in this space. And each university at LabsLand has its own space. Like for example, Rene, if you want, I can show yours first, like the University of Washington space, so that you can see like how each university has its own space. They can control the groups, which is the group when like they can control the statistics, like who has used what laboratory at what time of the day, how many students, how many accesses, like all these things like can be are seen by the instructors of the university. In this case, we created a space only for this workshop, so we will provide you a link to be able to test it. And here we added several laboratories, including the Intel D1 system on chip and the D215 and the FPGA laboratory, which actually uses these other two laboratories. But we also added in the demo other types of laboratories. So Rene, if you want, I'm going to access this one, and you can guide.
I will guide, yeah. Okay. So what we will be seeing is this is a web interface where students can either write their code. So just to go back a little bit, the course that I teach is digital design using FPGA, where students are expected to write or implement their design using a hardware description language like System Verilog, and this is what we are using. So students write their System Verilog on a tool like Quartus, and they actually have local copies on their computer from the software from the Quartus, and where they do the development and the testing, and then when they are the simulation. And when they are ready to actually run the code on a real FPGA, that's when they take the program to this web interface. As you can see, this code editor, they can upload their code directly, or they can edit it here. And this is not taking any time from the FPGA live session. So they can take their time here doing whatever they want, but they usually do this like prior to coming to the LabsLand network on their local machine. So now this is a very basic System Verilog program that implements a full adder example, and now it can be sensitized. So if we push sensitize, this is the compilation happening here, and it's throwing here, like, you know, it's successful. If there was any error, then we would see that there is an error that the students need to fix it. Successful. Now it's time to upload to the FPGA, and that's when it goes to reserve one of the FPGA boards. And now, as you can see at the top, this is the logo of the Electrical Computer Engineering, which shows that this FPGA is located at the University of Washington. So if I was at UW, I would have waved, or, you know, just to say, yeah, hey, I'm here. This is actually at the University of Washington. But believe us, this is physically there. So as you can see here, these keys and these virtual buttons emulates the switches and the keys that are present on the FPGA. So we don't have to worry about, okay, how can we even, you know, flip the switch up and down? Do we need to be present next to the FPGA? No, we don't. So that part is emulated with the these blue switches. And so the code is running. The code that was compiled in the previous code editor works, and the result is basically showing, and you know, on the LEDs. And so students get 2 minutes. You see here a timer, and it's counting down. And so that's they have 2 minutes to run their program. And if everything looks good, they are done. They can leave the session if they are done before the timer times out. So so this is a very, very simple example of system Verilog code. But in my course, it's the advanced, the digital design. And so students write comprehensive code and more complicated code that is just not suitable for the purpose of the workshop, where we don't have much time to show a lot. But my students were able to just to share some of the labs that they were able to finish. They designed, for example, an occupancy counter, a parking lot occupancy counter that simulates the entrance and exits of cars. They were able to implement line drawing algorithm and also animation of line patterns on VGA display. They were able to use audio and apply some signal processing algorithms and filtering to enhance the audio. They were also able to create more sophisticated projects using game controllers that interfaces VGA, an 8 controller or audio or keyboard or joystick. So and pretty much all of these, they always had 2 minutes access to run their code on the real FPGA. And so now I will go back to my slides. So if you can,
yes,
sharing, Pablo, please.
I was showing the VGA part of
the VGA. Perfect.
Just to show, like, this is the VGA coming from the FPGA. This is if you notice, this is a different FPGA than before. But basically, given that there are many copies at UW, then we randomly are assigned to one or the other. This is the standard example that comes with the D1 system on chip, and it's just to show that I mean, like, in this case there is nothing with the switches and so on, but in this case you can see that like how the VGA output from the FPGA board is actually portrayed in real time in the web interface. So I'm going to stop sharing.
All right, thank you. And continue. All right. So students' feedback in the end of the autumn quarter. This question was in my course evaluations, asking students to rate their experience of using, excuse me, using the remote lab. That was when we first implemented the remote lab, and the response was very positive and very supportive of, I mean, I had 60 students and 47 out of 60 students filled the survey. And for that question, it's very favorable. So students rated the remote lab favorably. And also they strongly supported the expansion of this remote lab. So now we currently have 8 boards up and running. And so I thought about, let's expand it with more FPGA labs or more FPGA boards. And that was resulted in an internal grant from the UW Students Technology Fees. And this STF is an entirely student-operated organization. They make the decision, and because of the students who supported the idea very strongly, they approved so that we can buy more equipment and have more than just 8, and which is what we are working on right now. And by the fall, beginning of the fall, we should have in our network at UW, instead of 8, we should have about 36 Intel FPGA boards. Learning outcome, it was interesting. You know, this solution obviously was very convenient, solved big logistics problem during the COVID, but then remained the question, is this a scalable solution? Is this a solution that we can actually rely on after COVID-19? So it was very important to assess the learning outcome. And I am actually, right after this session, I'm going to jump to my next presentation to present my paper, and it's the remote versus in-hand hardware lab in digital circuit courses, where it shows actually that the learning outcome was not compromised, and in some cases it was even better in the remote lab setting. So that is good news, and that was encouraging for me to expand the remote lab at UW and also to continue using it after COVID and completely eliminate the need for shipping or maintaining lab kits. And so that is the learning outcome. Because of this study, which I invite you all to join my next session or read the paper if you are interested to learn the details about the learning outcome. Future work, I mentioned we are working on expanding the remote lab to add more FPGA boards. We are also working on supporting more features like adding sensors, video input, and more, so we can give more sophisticated experience to students working on digital design. More evaluation of the effectiveness, similar to the paper that I will be presenting shortly, and then also working on developing curriculum for equitable access to industry-grade hardware, and using this remote lab as a solution to promote equitable access to resources. Recognition, good news about this distributed lab between the 5 universities. We were recognized in the Remote Engineering and Virtual Instrumentation Conference of 2021, and we were awarded the Global Online Lab Consortium Award, and that was great. We're very proud of that. And we were also featured in IEEE Spectrum, June. This is the June issue of 2021. So this is the cover page. So we are there in the print, in the magazine. With that, thank you very much for being here and for giving us the opportunity to share our experience. And again, thank you to Intel for sponsoring this session and for inviting us to share our experience. And with that, we are open to questions. And here is the link if you want to create an account to test the remote lab yourself.
Also, I think that maybe you cannot write questions in the chat of Zoom. However, in the website in padable.co, in the website of ASEE, you can actually write questions. And actually, Professor Tahmina, I hope I'm pronouncing your, I'm sorry if I don't pronounce the name correctly. She was asking, does this mean that these FPGAs are physically powered all the time so they can run the code virtually from anywhere? Rania, if you want to.
Yes, they are powered and running all the time. That is correct. Are there other questions?
Not so far. She was asked for email address. I'm going to add also yours is
RHUSSEIN.
Yes, at
uw.edu.
Perfect. So I also added that one in the chat. And I don't know, Rania, do you want to explain also anything else about the the space, for example, or how you use it, or like anything else about the experience at UW?
So actually, that was a very good question about, do they need to be powered up all the time? And the answer is yes, which may seem like, oh, so they are up all the time. Is this a good thing or a bad thing? I guess, you know, there is always a trade-off. But looking at the scalability of the problem, I have 8 boards up and running, and we're able to serve the 60 students in a classroom, compared to the traditional way of doing that. Each of the 60 students would have got an FPGA board either shipped to them or picking it up, and then they will have to worry about maintenance, or if the board goes bad or any of the components goes bad, then they need to come or contact the the lab technician for a replacement, which may happen anytime. And so this, the availability of the 24/7 support is not available when we were using the physical boards. Whereas for the remote lab, anytime, regardless of where the students are, they don't need to worry about maintenance. They don't need to worry about having a space at home. And this can be equitable issues, to have the lab physical components at home. It's available for them. And more importantly, one of the main reason I wanted to push for this solution to continue, and I plan to continue doing it, is that in the past, students had access to an industry-grade hardware while they are registered in the course. But once the course ends, they had to return the lab kit, and they don't have access to an FPGA board, which is expensive. I mean, we're talking about maybe a couple $100 to get an FPGA. So students who want to expand their skill set or want to work on extracurricular activities may not be able to do this unless they can afford buying industry-grade hardware, which they don't need to do that with the remote lab because it's available for UW students. They can access it. It's available for them 24/7. So it's a cost-efficient and, in my opinion, equitable solution. So I hope I answered your question.
One major comment on that is that so far we have expanded always the network kind of horizontally, meaning that adding more university to the network, and each university doesn't have a big number of laboratories. Like that is changing, but mostly it has been like that, and therefore like it was not a priority to complex systems where we unpower, like turn off the power of certain devices while they are not being used or something like that. Technically, it will be possible to do it, and that will be like an interesting idea as it grows vertically, like meaning more laboratories per university. So, for example, Rania, maybe in your case, like it will be possible to say, like, okay, like if there are, I don't know, 30 something FPGAs, like we only have like 4 up and running, and whenever there is demand, then we automatically turn on the others or something like that. That will be possible in the future, but it's not something that we are like, it's not a high priority right now.
Yeah.
It's 1 minute left, so.
Yes, and we were told that the session ends automatically, I think. So we want to wrap up before we got cut out. So are there any questions? And you are all very welcome to, feel free to email me or Pablo. We put our email where in the chat. And you can also find me on, the University of Washington's ASEE department's faculty page, and you can anytime feel free to reach out to me if you have any questions. And again, I invite you, whoever is able to join my next session to present the paper on the assessment of the learning outcome using the remote lab compared to traditional lab. With that, thank you very much. If there are no questions, it was a pleasure being with you. Thank you for the opportunity. And thank you, Intel. Thank you, everyone.
Thank you. Thank you, Ryan, for being here, and thank you also, Intel. Okay, so I think we can close this session and run to the other one.